Hi everyone, thank you for watching this video. I'm going to talk about our group machine learning final project, which is CitiBike transportation management. Nowadays, the bike sharing system has gradually become an important part of the urban transportation system. CitiBike, a bike sharing program launched by the New York City government and sponsored by Citigroup Incorporation, is one of the most popular bike sharing systems in the world. Generally speaking, a public bike sharing system is that it allows users to ride rented bicycles from one station to another. However, city bikes' popularity also results in a high demand that some stations regularly lack bikes while other stations are completely full, make it hard to take or park a city bike. Therefore, to avoid such problem, dozens of rebalancing teams, for example, like trucks and bicycle trailers, are used to reallocate bikes by shuttling bikes among full and empty stations. In our project, the most significant objective is improving city bike transportation management. In other words, we need to deal with the imbalanced situation. To be as an administrator of CitiBike, we want to optimize the bike reallocation problem by raising the following three questions. What is the total number of bikes being used in the system at any time? How do the bikes inflow or outflow at a given station at any time? How to reallocate bikes between stations due to unbalanced in or outflow? Here is our dataset. The CitiBike trip dataset comes from CitiBike official website. The NYC climate datasets come from NOAA, which is National Center for Environmental Information. We will see the detail of these two datasets in the following pages. This is the CitiBike trip dataset. It contains information about trip details like trip duration, start time, stop time, and bike ID. It also contains the information about start station and end station, like their station ID, station name, station latitude, and station longitude. This is the NYC climate dataset. We only use TEMP, which means temperature, SPD, which means wind speed, and PCPO1, which means rainfall index. We only use these three indexes in this dataset. Here is our algorithms. We do regression on total number of bikes. We also do regression on inflow or outflow of bikes at one station. We do SVM to predict inflow or outflow of bikes at one station. SVM means super vector machine, which analyzes data used for classification and regression analysis. We do clusterings, which means that for cluster analysis, which is a method for statistic data analysis. First, we look regression on total number of bikes. Since the data in original dataset is per travel, we transfer the data into per hour. We introduce two dummy variables, time of the day and day of the week. Furthermore, we introduce some other explanatory variables like temperature, wind speed, and rainfall, which we have discussed before. Finally, we do multi-variable regression models. This is the outcome of regression on total number of bikes. We can see the R-square and adjusted R-square is around 65%, which means the model explains most of the total number of bikes. The training and the test MSE is large because the response variable has a large scale. Then we look regression on inflow or outflow of bikes at one station. Here we introduce night flow concept, which equals to inflow minus outflow. Since there are 498 stations, we just choose 10 random stations, then build multivariable regression model. We can see that this regression model cannot explain the net flow very well enough because the R-square and the adjusted R-square are low. This is because the inflow or outflow at one station is gradually not stable, and it might be affected by many random factors that it is hard to capture. Then we introduce SVM to predict in or outflow of bikes at one station. Instead of predicting the number of flow, we try to predict if the station has an inflow, outflow, or a balanced flow during a time interval. To achieve this, we categorize the flows into three catalogs: -1, 0, and 1. The outcome of this model works much better than regression, but still needs to improvement. So, in order to make some improvement, we introduce clustering. Generally speaking, we will try to do the prediction on clustered dataset, since temperature, weather, time of day, and the day of week would be more likely to impact a group of stations rather than a single station. To predict the inflow or outflow after clustering seems more reasonable. Comparing to predict the inflow or outflow for just one station, predicting the station in group might stabilize the inflow or outflow across stations, which might give a better predicting result. Here we have two graphs. The left graph represents average cohesion with clusters. The right graph represents average separation with clusters. Here, we do regressions on inflow-outflow of bikes of clusters. The outcome is that we can see the most of the R-square and adjusted R-square are larger than regression on inflow or outflow of bikes in one station, which means after clustering, the performance of gradual regression model is better than individual regression. But in general, since the R-square and adjusted R-square are still relatively low, we should use other methods. What we should use is the super vector machine to predict inflow or outflow of bikes of clusters. We can see that in general, the performance of super vector machine on clusters are better than on one single station. This is the station map after clustering. We clustering the stations into 18 groups. Finally, our primary conclusion is that, first of all, the regression model to predict the total number of bikes being used in the system works well. Secondly, the regression model to predict the night flow of different stations does not work very well. After that, multi-class super vector machine worked better than regression but still need to be improved. Finally, after clustering, both regression and the multi-class super vector machine on clusters are more likely to perform better. However, there are still some problems in our projects. We need to fix the following problems. First, in our model, there are some underestimates for the first quarter in 2015. The second problem is that there miss extremely peaks during summer. The third problem is that high level of out-of-sample loss for some clusters. As far as we are concerned, by adding more explanatory variables, such as snow days, holiday, and big events, can improve our models to be more accuracy. Thank you very much for watching this video.